Hello everyone and welcome. In this video we're going to talk about the Euler-Mascheroni constant and we're going to express it as the sum of a series. So we're going to start with the definition of the Euler-Mascheroni constant. So the Euler-Mascheroni constant, denoted by the lowercase Greek letter gamma, is defined as the limit of h sub n minus natural log of n, where h sub n is the nth harmonic number. So the question that comes in my mind is, the first question is, does the limit actually exist? So let's prove that before we can actually go any further. Okay, so we're going to look at the quantity h sub n minus natural log of n. So in order to do that, let's start with two integers k and n, such that k is between 1 and n. And then we're going to choose a real number x between k and k plus 1, so that 1 over x is going to be trapped between 1 over k plus 1 and 1 over k. Now, if we integrate from k to k plus 1, using the fact that an antiderivative of 1 over x is given by natural log of x, we're going to get this compound inequality. Now we can take the sum as k goes from 1 to n minus 1, and using the fact that the middle term is actually telescoping sum, we get the following. So we get h sub n minus 1 is less than or equal to natural log of n, which is less than or equal to h sub n minus 1 over n. Now we want to bring the quantity h sub n minus natural log of n in the middle of our compound inequality. And that's going to bring us to this. 1 over n is less than or equal to h sub n minus natural log of n, which is less than or equal to 1. Because 1 over n is positive, well, we know that the sequence u sub n, which is given by h sub n minus natural log of n, is actually bounded. Okay, so we have a bounded sequence. What can we do with that? Well, all we have to do now is prove that our sequence is actually monotonic. So we are going to compute the quantity u sub n plus 1 minus u sub n. Now, using the definition of h sub n and using the quotient rule for logarithms, we're going to get that this is equal to 1 over n plus 1 plus natural log of 1 minus 1 over n plus 1. Then we can use the power series expansion of natural log of 1 minus x. And we're going to get the following. Okay, now notice that the first term in our infinite sum is precisely 1 over n plus 1. So we're going to end up with negative the sum as p goes from 2 to infinity of 1 over p times n plus 1 to the p. Now, everything here is negative because all the terms of our infinite sum are positive. So the whole thing is negative, which means our sequence is actually decreasing. Now we have a sequence that is bounded and decreasing, therefore it's convergent. Okay, and the limit of our sequence is precisely the Euler-Mascheroni constant. Its approximate value is 0.577 and so on. Okay, now we want to express this constant as the sum of an infinite series. In order to do that, we're going to introduce another sequence. So we're going to consider the sequence a sub n, which is a slight modification of the sequence u sub n. Instead of natural log of n, we now have natural log of n plus 1. So the first thing we want to check here is that a sub n and u sub n have the same limit. Okay, so we're going to rewrite a sub n as u sub n minus u sub n minus a sub n. Okay, so all we did here is introduce 0. Now, the difference u sub n minus a sub n is actually the difference of two logarithms, and it can be written as negative, log of 1 plus 1 over n. And now we can take the limit. Now notice that natural log of 1 plus 1 over n tends to 0, I mean, it tends to natural log of 1, which is 0, and u sub n tends to gamma, so the limit of a sub n is also gamma. Okay, now we want to express gamma as a series. And the starting point is actually this sequence a sub n. So a sub n is going to be written as a sum. Okay. Notice that natural log of n plus 1 can be written as a telescoping sum. So the sum as k goes from 1 to n of natural log of k plus 1 minus natural log of k. And then we can combine these two logs using the quotient rule and finally combine the two sums. Okay, so as we combine the two sums, we get the following. Now, if we take the limit on the left, we're going to get gamma, obviously, because the limit of a sub n is gamma. But on the right-hand side, we're going to get an infinite series. So gamma is the sum as k goes from 1 to infinity of 1 over k minus natural log of 1 plus 1 over k. Okay. Now, we're not going to stop here. We want to write this using the Riemann zeta function. Okay, so in order to do that, we're going to consider a sub n again. And then we want to use the power series expansion of natural log of 1 plus x. There. And notice that the first term in our infinite sum is precisely 1 over k. So we can simplify that and end up with the following. Now, we can simply interchange the order of the summation because one of the sums is finite. So we get the following. Now, if we take the limit on both sides, on the left-hand side, we get gamma. On the other side, we're going to get the following, which is simply the sum as m goes from 2 to infinity of negative 1 to the m divided by m times the sum as k goes from 1 to infinity of 1 over k to the m. Well, the sum as k goes from 1 to infinity of 1 over k to the m can be expressed as the Riemann zeta function evaluated at m. So we're going to get that gamma is actually equal to the sum as m goes from 2 to infinity of negative 1 to the m divided by m times zeta of m. So we just proved that gamma is actually equal to these two series. And I think this is a good place to stop. Thank you for watching and see you next time. Bye.